If you choose to sing this song for extra credit, the lyrics and the animation can be found on my webpage. Simply go to Chemistry, Elements and Animations, and Lyrics. Select your connection speed.
There's antimony, arsenic, aluminum, selenium, and hydrogen, and oxygen, and nitrogen, and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, chromium, lithium, beryllium, and barium. There's holmium and helium and hafnium and erbium and phosphorus and francium and fluorine and terbium and manganese and mercury, molybdenum and magnesium, dysprosium and scandium and cerium and cesium and lead, praseodymium and platinum, plutonium, palladium, promethium, potassium, polonium and tantalum, technetium, titanium, tellurium and cadmium and calcium and chromium and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, krypton, radon, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard, and there may be many others, but they haven't been discovered.
To access the lyrics, simply scroll down on this same page when it's done playing, and there's a PDF file that will have all the lyrics to the song. You may sing this individually for me at lunch with the music playing in the background and the lyrics in your hand, or you can sing it with someone else and do a duet. We know that it's organized according to what? Atomic number. The 1, 2, so forth, okay? That's how it's organized. And coincidentally, what kind of goes along with that? Not only the atomic number, but the atomic mass and number of protons. Good. But you're going to get some of that information we already covered again in the video, so you watch for that. Maybe you didn't get it in your notes now, you can, but you're going to learn some other new terms, like isotopes is one of the new terms you'll hear. Look for those. But what I want to do right now is just take a look at this assignment, because you're going to get your answers to this as you're watching the video, and I want you to be able to kind of pre-read and predict. Okay, it says number 1 and 2, you're going to be numbering the families and numbering the periods. Well, you can probably figure out what that is already. There's little spaces there to number. But we put the stuff, the elements, into groups because of similarities. They look alike, they behave in a similar way, they look similar physically, or have similarities physically, and they have similarities chemically. They combine and they do a lot of the same things when they're in the same group. Okay? Then down below that, number 3, you're going to be color coding this drawing with green, blue, and orange. If you don't have green, blue, or orange with you here today, then you're going to have to just try to lightly indicate in there with pencil what colors go where, and then you can go over it with, or erase it and go over it with colored pencils at home. If you don't have colored pencils at home, come in immediately after school at 1:55, and I will give you some colored pencils you can check out, which you have to return. But you're going to be coloring all the metals green, all the metalloids blue, and all the non-metals orange. They'll talk about what those are in the video, okay? And there are what are called alkali metals. Those will just be plain green. Alkaline earth metals will be green but have vertical lines going through them. And transition metals will be green but have horizontal lines going through them. The metalloids just plain old blue. And the non-metals will all be orange, but if they are halogens, they're going to have vertical lines. And if they are noble gases, they're going to have horizontal lines. You'll need to put a heavy, dark zigzag line like I showed there, okay? Dark zigzag line like this. Make it nice and dark, and it'll separate some blocks. So like you'll have, a block here. It'll have some element in it, and another block here, and another block here. So you're saying that all the stuff on this side is metals, all the stuff on that side of the zigzag line are non-metals. So you're going to be doing that as well. Then on to the back. Once you know what the different group names are, groups are sometimes referred to as families. And the family or group name will go in the space below each frame. In the frame you have the family members. Some of them are already shown there. Their abbreviation is already there. You have to figure out what the remaining members are and fill in the abbreviations in those heads. I don't care which head they go in as long as it's one in the correct frame. Okay? Any questions on this? Great. The videos are kind of old, kind of annoying music, but they have good content. First one's about 9 minutes.
In the middle of the 19th century, before modern chemistry was established, a number of scientists experimenting with materials came to understand that matter was made up of different elements. They found that some elements were very similar, while others were radically different. What they could not understand was why these differences existed. Solving this mystery led to the development of the periodic table of the elements, which remains the major analytical tool of chemistry. Ancient metalworkers were perhaps the first to learn about the elements. Gold, silver, copper, and iron were forged in foundries as long ago as ancient times. By 1800, some 30 elements were known, and over the next 100 years, over 60 elements had been identified. As they studied these elements, scientists looked for patterns and how the different elements related together. In 1869, a Russian chemist, Dmitry Mendeleev, published this table of all the known elements. It is the forerunner of the periodic table we use today and one of the most brilliant insights in science. Mendeleev's table was based on the increasing atomic mass of the elements. As he arranged the elements in his table, he found that some had similar properties. Those he arranged in vertical columns in his table. He also recognized that there were gaps in the patterns of the elements, and predicted that there were undiscovered elements that must fill those gaps. Later, new elements were discovered that fit his predictions. Today, we do not list the elements in the periodic table by their atomic mass. We list them by atomic number. The number of protons in the nucleus of the atom determines the atomic number of an element. The person who saw the importance of atomic number was a young English scientist by the name of Henry Moseley. He was a student of Ernest Rutherford, who had discovered the nucleus and gave a preliminary explanation of the atomic structure. Moseley understood that the significant difference between the elements was their number of protons. Once the number of protons is known, it is possible to determine the number of electrons in a neutral atom. It was not that Mendeleev was wrong in the way that he listed the elements. The atomic mass of elements increases as the number of protons in the nucleus increases, but atomic number tells us more about the element. The periodic law is the basis of the periodic table. It states, when elements are arranged in order of increasing atomic number, their physical and chemical properties show a periodic pattern. As we will see, the pattern of the table is tied to the very structure of the atom itself. That is what makes it such a useful tool. The periodic table is a type of map of all the elements. The position of the element on the table explains the structure of the atom and helps us understand how it will react with the other elements. The elements are organized from atomic number 1, hydrogen, to atomic number 114, unquadium. Actually, there are only 92 elements that are found naturally in the universe. Uranium is atomic number 92. Beyond uranium are the transuranium elements, which have only been created in laboratories. The elements are organized in horizontal rows called periods. The numbers of the periods are printed along the side. They are called the principal quantum numbers, or simply N. In period 1, there are only 2 elements, hydrogen on the extreme left and helium on the extreme right-hand side of the table. Periods 2 and 3 each have 8 elements. Periods 4 and 5 have 18 elements. Period 6 has 32, and period 7 goes from element 87 to 114 on this table. Where are the extra elements in periods 6 and 7? They are printed below for convenience, because that is the only way they can be fitted on the page. Not only is the position of the element in the period significant, but so is its position on the vertical column. These columns are called groups. Their numbers are listed along the top of the table. Elements in each of these groups have similar characteristics, and because of this, they have been given names. The elements in group 1, for example, are called the alkali metals, and group 18 are called the noble gases. The size, or radius, of atoms is an important factor in their bonding. The radius of elements decreases from left to right across each period of the periodic table. The numbers of electrons increase across the period from left to right, but there is also an increase in the nuclear charge due to the additional protons in the nucleus, which hold the electrons more tightly to the nucleus. The radius of elements also increases moving down the groups of elements. This is because there are more electrons, protons, and neutrons in the atoms. There is one element that is unique. It is hydrogen, atomic number 1, the most prevalent element in the universe. Hydrogen is listed in group 1, but it is separated a little from the others. It has many of the characteristics of the other elements in group 1, the alkali metals, but it is a gas and definitely not a metal. Every element has its own square in the periodic table, and within that square is contained the vital information of the element. This is the square of nitrogen. Its atomic number of 7 is written at the top. We immediately know that there are 7 protons in the nucleus of the atom, and when it is electrically neutral, the element has 7 electrons. Every element has a symbol that is used by chemists around the world. Some periodic tables, like this one, have the name of the elements, but many do not. Nitrogen's symbol is N, and uranium's is U, but not all of the symbols are that easy to remember. Gold, for example, is AU, which comes from the Latin word for gold, aurum. Some of the more rare elements are named after countries where they were discovered, or scientists. Chemical formulas are always written using the letter symbols, so it is helpful to remember some of the most common ones. The atomic mass of the element is the number written immediately below the symbol and name of the element. Nitrogen, for example, has an atomic mass of 14.0067 AMU. AMU stands for Atomic Mass Unit. Chemists often need to know the atomic mass of an element in order to accurately measure the quantity of substances. The atomic mass of elements almost always increases as the atomic number increases. The reason is that as the atomic number increases, there are more protons, neutrons, and electrons in the atom. Each proton or neutron equals about 1 AMU. Electrons have much smaller mass. As a result, the higher the atomic number, the greater the mass of the element. The last number at the bottom of each square describes the electron configuration of the element. The nucleus.
Okay, we're not going to get into electron configurations yet. We are going to get to it eventually, and it can get a little confusing, a little complicated, so I want to save that for right now. But where the electrons are located, how many there are, is very important in how elements will react with other elements. This one's going to be about 17 minutes and has a quiz at the end. What country do you think that narrator was from? I kept saying hello.
Oh, Canada.
Canada, yeah.
Canada. We have to take the quiz.
Yes. That's some great xylophone there. Yeah, I know. Don't we all?
What makes one substance different from another? What makes the glass in these goblets different from the diamond in this ring? They are both clear, sparkling solids, but diamonds are one of the hardest materials on Earth and are even used to make saws which can cut rock. And glass is fragile, easily broken. The difference lies in the types of atoms that make them up. What makes atoms different from each other? We are going to take a look inside atoms and examine their atomic structure. Atomic structure refers to the arrangement and number of smaller particles of an atom. These smaller particles that make up atoms, or subatomic particles, include protons, neutrons, and electrons. Let us consider each subatomic particle separately. This is an atom of carbon, a substance found in charcoal and diamonds. The nucleus is the center or core of the atom. It is where 99.9% of an atom's weight is located. The nucleus contains protons, as seen here in red, and neutrons, seen here in green. Protons are positively charged particles, symbolized here by a plus sign. All protons are the same, no matter what type of atom they are in. The weight of subatomic particles is measured in units called atomic mass units. A proton weighs 1 atomic mass unit. There are millions and millions of protons in a single drop of water. The other subatomic particles located in the nucleus are neutrons. A neutron is a neutrally charged particle. They do not have a charge. Neutrons also have an atomic mass of about 1 atomic mass unit. While the nucleus contains most of the mass of an atom, it takes up only 1/100,000th of an atom's space, equivalent in ratio to this ball in this meadow. While all atoms have a nucleus, what is it that makes them different? The answer lies in their number of protons. The atomic number is the number of protons in an atom. For example, the element carbon, which is what makes up the graphite in this pencil, has an atomic number of 6. It has 6 protons. All atoms of carbon have the same atomic number of 6. The atomic number also equals the number of electrons. Therefore, carbon also has 6 electrons, seen here in red. Copper, a different element, has an atomic number of 20. It is useful to know the combined number of protons and neutrons in an atom. The atomic mass, also known as the atomic weight or mass number, is the sum weight of the protons and neutrons in an atom. Let's take the element silicon, symbolized by the letters Si. Silicon is a major element that makes up the sand on this beach. Silicon has 14 protons and 14 neutrons that add up to an atomic weight of 28 atomic mass units. While most types of carbon, such as that in these trees, have 6 protons, the number of neutrons may vary. Isotopes are atoms of the same element with different numbers of neutrons. For example, carbon can have an atomic mass of 12 or 14. Carbon with an atomic mass of 12, seen here with 6 red protons and 6 blue neutrons, is referred to as carbon-12. But carbon can also have an atomic mass of 14, called carbon-14, seen here with 6 red protons and 8 blue neutrons. Carbon-14 in nature is unstable and gradually deteriorates. With specialized equipment, scientists can estimate the age of objects, such as this bone, by measuring the degradation of carbon-14. Because most elements have more than one isotope, each element has an average atomic mass, calculated from the average mass of its isotopes. The fast-moving particles around the nucleus are electrons. Electrons are negatively charged particles. They are a fraction of the size of protons or neutrons. To help you visualize this size difference, if this ball were a neutron, then this P would be an electron. An electron weighs just 0.0006 atomic mass units. Because electrons weigh so little, their weight is not even considered in calculating an atom's atomic mass. The electrons move very quickly, perhaps as quickly as 1 billion times a second around the nucleus, forming what is called an electron cloud. The electron cloud is the space in which the extremely fast-moving electrons are likely to be found. As scientists learned more about elements and atoms, they developed a way to organize them in a logical manner. They created a chart to organize elements by their atomic structure that is referred to as the modern periodic table. The modern periodic table represents a remarkable scientific endeavor. It takes thousands of seemingly unrelated pieces of information and fits them together in a logical format. This organization is dictated by the periodic law, which states that both chemical and physical properties of elements are periodic functions of their atomic numbers. The position of elements on the periodic table is dictated by the number of protons, or their atomic number. Notice how the top number, the atomic number, increases from left to right. The elements on the periodic table are represented by their chemical symbols. A chemical symbol is an abbreviated way of symbolizing an element with 1 or 2 letters. For example, the element oxygen, found in the air we breathe, is symbolized by the letter O on the periodic table. Oxygen, along with hydrogen, is a fuel commonly used in rockets. Hydrogen is symbolized by the letter H, found in the upper left portion of the chart. Let's take a look at another element, calcium. Calcium is an element found in the human body and in the bones of other animals. Calcium is also common in rocks, such as limestone and marble seen here. It is located here on the periodic table. The chemical symbol for calcium is Ca. On top of the chemical symbol is the atomic number. The atomic number of calcium is 20. Remember that the atomic number is equal to the number of protons. Here you can see 20 protons with a positive charge in the nucleus. Below the chemical symbol for calcium is the atomic mass. Here you can see that the atomic mass of calcium is 40.08 atomic mass units. You will notice that the periodic table is organized in a grid with rows and columns. There are 18 columns called groups or families. These groups or families have elements that possess many similar chemical and physical characteristics that we will explore later. The rows in the periodic table are called periods. Unlike the elements in families, the elements in periods do not have a great deal in common. But by looking at elements across the periods, we notice some interesting patterns. There are 7 periods or rows. Notice that a portion of rows 6 and 7 has been removed. These periods are still part of the periodic table, but have been moved to make the table shorter and easier to read. As you go from left to right in the periodic table, one obvious trait stands out. The atomic numbers increase in regular intervals. For example, you see how the atomic number increases starting with silicon with an atomic number of 14, then phosphorus with an atomic number of 15, then sulfur with an atomic number of 16, and so on. Of the 109 known elements, the vast majority are metals. These are highlighted on the periodic table in green. While you may think of objects such as silverware, pans, and wires as metals, other elements, such as calcium and sodium, are also metals. Elements toward the middle and left, such as mercury, are also metals having metal-like properties, such as shininess, as seen in this aluminum foil, and are malleable, the ability to be shaped. Metals are also good conductors of electricity, such as that found in this electric fence. Generally speaking, metals also have a high density, as is the case with this piece of rapidly sinking lead. Magnesium, a metal commonly used to make airplanes, is in a specific family of metals called the alkaline earth metals, highlighted here in blue on the periodic table. The alkaline earth metals are a highly reactive group. For example, magnesium, seen here, brightly reacts when burned. Within the metals are the transition metals, seen here in green. They are less reactive than the first 2 groups of metals. There are many commonly used metals in the transition metals, including iron, used in making machinery and bridges, copper, used in wires and pipes, and tungsten, used in light bulbs. These shiny metals tend to be good conductors of electricity. Transition metals, such as iron, zinc, and cobalt, are also used to make colorful paints. The elements to the right of the staircase-like line in the periodic table are called the nonmetals. The nonmetals tend to have opposite properties from the metals. These elements tend to have a dull luster and are brittle, such as this sulfur. They have low densities and melt at lower temperatures. They do not conduct electricity well. One such family of nonmetals are the noble gases, highlighted here in light red. These elements are found in small amounts as gases in the Earth's atmosphere. Argon is the most common of the noble gases and makes up about 1% of the Earth's atmosphere. Many signs are made with inert gases, such as this neon-filled sign. The elements highlighted in orange, just to the right and left of the staircase line, are called metalloids because they have properties of both metals and nonmetals. Metalloids are solids that conduct heat and electricity better than nonmetals, but not as well as metals. Silicon is one such metalloid that is used in computers. It is valued in computers because it is a semiconductor, meaning it is somewhere between a conductor and an insulator of electricity. We have explored just a small amount of the information found on the periodic table. Next time you get a chance, spend some time exploring the periodic table. You will be surprised at the amount of interesting facts you will learn.
So they do the quiz with a little beep sound to replace the blank for fill in the blank. Please don't get carried away with laughter because he's not cursing every time you hear the little beep sound, okay? Let's see how you do. There are 10 questions.
Fill in the correct word when you hear this tone. Good luck, and let's get started. Number
You're
one,
not writing anything
atomic refers to the arrangement and number of smaller particles in an atom.
Configuration.
Number two, the is the center or core of an atom.
Nucleus, yes.
Was the other one mass?
Configuration.
Number three, are positively charged particles located in the nucleus.
Protons, yep.
Number four, neutrons have a charge.
No, why that's so funny?
Zero.
Have a neutral or no charge.
Number five, are atoms of the same element with different numbers of neutrons.
It's really not that funny, guys.
Because, well, you've seen it a couple times over and over again, so.
You watch Family Guy.
So have you. This is the 5th time. What are they?
Number six, are subatomic particles with a negative
What was the answer to the last one? Isotopes.
charge.
Electrons.
Yep.
Number seven, the sum weight of protons and neutrons in an atom is its atomic
Atomic what? Mass. What's atomic mass measured in? What units?
number eight.
AMU.
Elements in the periodic table are ordered according to their atomic
Number, yes. No, it's really not that funny. It amazes me every year that people laugh at that.
number nine. Are the most common elements on the periodic table.
Metals. Large portion of your table should be green. Last one.
Number 10. Elements in the family called the alkaline earth metals are very
Alkaline earth metals are very what? Well, if you listen carefully, he talked about how reactive they are. How some of those metals can just be exposed to air and they might burst into flames. Very reactive, okay?
Oh, is that includes?
So, we're going to quickly review some of the main ideas that you should have gotten and should have gotten in your notes. You learned a little bit of history about Mendeleev, the Russian that looks kind of like a madman there from that picture. But he's the one that first realized, hey, all these building blocks of matter, all these elements, they have some stuff in common. And he put them into this first, what we call the periodic table, this first group. And what it allows you to do is it allows you to make predictions. When I take this and this, if this belongs to this group and this belongs to this group and I put them together, I'm going to get a certain kind of thing. That's the whole point of that table that I gave you, okay? So that was Mendeleev. Now, he did not organize it the way we currently do. We organize it today based on what? Atomic number, which is the number of?
Electrons and protons.
Yep, electrons and protons. Good. Okay, so when we look at this little animation, I really like this one because it really gives you a sense of what's going on in the atom. Right now I've got an empty atom. I can fill in, I can put the stuff in the center part known as the nucleus, and I can put stuff around the outside. Some of these particles have mass, some do not. What doesn't have mass? Electrons. They actually do, but it's so tiny that it hardly even counts, so we don't factor it in. The protons and neutrons do have mass. So every time I add them to the center, to the nucleus, you'll see the mass number go up. But the most important number, the one that determines the kind of atom it is which number? Which number? Yeah, the protons, which also determines what?
Tell us mass, atomic number.
Yeah, well, you're right. It determines these two as well. But the atomic number is the all-important one. That's the one that tells me the kind of matter it is. So if I take one proton and I put it out here on the page, what have I just created?
Hydrogen.
Hydrogen, the most basic kind of matter, hydrogen. Now, notice the mass is 1, okay? But what's important in determining the kind of matter is what that atomic number is. So now I take a neutron and I put it out there. What's going to happen to my mass?
It's heavier.
It gets heavier. I added another thing that has a mass of 1. And now the mass is twice as much, but is it still hydrogen?
Not helium.
It's hydrogen.
It is still hydrogen, guys. Look at the atomic number. Shh. Look at the atomic number. It's still hydrogen. Not until that number goes up to 2. I put another proton in. Now it became helium. The number of protons determines the type of atom. Okay? Sorry, I got rushed through this there. Okay? So if I put an electron out, will that affect the mass? No. But it will affect the charge. It went from +2 to +1. I put another one out there. What will the charge be? 0, neutral, okay? So what we see is that hydrogen can exist in several different forms. It can have one neutron. I can put a second neutron out there. If I put another neutron out there, I change its mass, right? That number's different, but the atomic number is still the same. Different versions of the same atom. I mean, when it has 2 protons, it's going to be helium, but a different version of that with more or less neutrons is called an isotope. And you should have gotten the definition for that. And by the way, guys, that's why those atomic mass numbers are decimals. Why they're not whole numbers. Because each one of the atoms has different varieties, different isotopes that can be created. If they have 3, and this one has a mass of 4, and this one has a mass of 5, and then you average them all together, that's how you end up with a decimal number. That's why it's not a whole number. Okay? All right, so these were the main concepts you should have gotten. You should have gotten that the periodic table is arranged according to the atomic number. As we add more protons, it goes from upper left, across, and then down towards the bottom right. And that the rows that go across this way, horizontal rows, are called periods. The ones that go up and down this way are called groups or families. One of them's a little older name than the other. And that we take a zigzag line and we separate the metals from the non-metals because they react differently. So on this periodic table, you should have a lot of it in green because there's a lot of metals. You should have a few in blue. I know that looks like green there. It's metalloids. And then some in orange that are the non-metals. In particular, the tricky ones are hydrogen. Notice how they separated it up here. Because it doesn't quite belong to this group or family in some respects. It's kind of its own separate thing. This is not a metal. If you color-coded that green, you're mistaken. Hydrogen is not a metal. Another one that people often get confused with is they drew the zigzag line in the right place. And they were told that the things on either side of the line are going to be what? Metalloids. But one of them next to that zigzag line is not a metalloid. Which one? Aluminum is not a metalloid. Aluminum is a metal. So you need to be careful with that. Okay? The other thing that you probably didn't hear in the video, they didn't talk about, they talked about noble gases, and we'll get into them more. They didn't talk about halogens. And halogens are all belonging to group number 17. Okay? So make sure you know which one that is and you color code it accordingly. Group number 17 are your halogens. Okay? Let's see here. Finally, When you do the backside, remember that the group or family name goes in this space, and then the abbreviation for all the members of that group goes in the empty heads that don't already have the ones in there.
Elements in the